Welcome to acid-base equilibria. In this video, we are going to discuss the definition of an acid and a base from some different perspectives, and then we're going to talk about what it means to be weak or strong in terms of acid in a solution. All acids exist in water, so when we're studying acids and bases, we're going to assume that everything is dissolved in water. And when we take a look at water, you might assume that all water is simply H2O. However, if you actually look closer, you'll find out that there is a very small percentage of H3O, or hydronium ions, and an equally small percentage of hydroxide ions. In fact, if we're looking at water with a pH of 7, which would be pure water, the concentration of hydronium is 1.0 times 10 to the negative 7th molar, and the concentration of hydroxide is going to be exactly the same. When we multiply those two together, that gives us something that we're going to call Kw, and that's 1 times 10 to the negative 14th. I'm going to talk about that in future videos, but for right now, what I want you to know is neutral water has some hydronium and some hydroxide in very small quantities. One of the most common definitions for an acid and a base is the Arrhenius definition. This is the definition that you likely learned in middle school, and that is that an acid is going to add hydrogen to water, and a base is going to add hydroxide to water. If we look at HCl and we add it to water, it's going to become an H3O plus, the H adding to the H2O, and Cl minus in the reaction. I also want to mention here, do we notice how this H is written in the front of the chemical formula? That suggests that that's what we call an acidic hydrogen, which means that it can come off when dissolved in water. The same thing happens with a base. We have direct dissociation. So the NaOH is going to split up into the sodium ion and the hydroxide ion. So an Arrhenius base is going to be a base that directly adds a hydroxide ion to the solution, making it more basic. And an Arrhenius acid is going to be an acid that directly adds hydrogen ion to the solution, making it more acidic. Not all chemicals that affect the hydrogen ion concentration or the hydroxide ion concentration do that by directly adding those ions to the solution. So we are actually going to turn to the Bronsted Lowry definition, which is going to give us a little bit of a broader definition. A hydrogen atom is, of course, made up of a proton and an electron. If we consider that a hydrogen ion doesn't have the electron, it becomes just a proton. So when we're looking at the Bronsted Lowry definition, an acid is something that's going to donate a proton, whereas a base is going to be something that accepts a proton. And in the equation, we're going to look at H plus as representing that proton. So let's look here. We have HCl, hydrochloric acid, and ammonia. If I find HCl over here and I look over here, it has lost a proton. That H is gone, and we know it was an H plus because we are left with this extra negative electron here. If I look at my ammonia, I go from having 3 hydrogens to having 4, as well as adding that positive charge. So we can see that the hydrogen ion started on the hydrochloric acid and ended on the ammonia. The way we might look at this relationship, or some terms we're going to use, is going to be the conjugate base and the conjugate acid. So we know that the acid, first off, is the one with the hydrogen in front, and it's also the one that loses a hydrogen. And the base is going to gain a hydrogen. Sometimes it will have a hydroxide on it, but sometimes not. Then if we look over to our definition of conjugate base, the conjugate base is going to be the acid without the proton. And specifically, we're going to look for both the conjugate acid and the conjugate base on the products side of the arrow. So in this case, the conjugate base is going to be the Cl minus. And then the conjugate acid is going to be the ammonium. Another way you might consider this is if I were looking at the reaction going in this direction. This gains a hydrogen, which means it's acting as a Bronsted base, and this species loses a hydrogen, meaning it's acting as a Bronsted acid, but it's written on what is considered the product side of the reaction. So we'll call it the conjugate base and the conjugate acid. So with Bronsted Lowry acids and bases, we have the acid, the base, the conjugate base, and the conjugate acid. Bases have conjugate acids, acids have conjugate bases. This is in contrast to the Arrhenius definition, where traditionally you have acid plus base yield water and a salt. Just in case you see this formula here, this comes from a different definition than the acid base conjugate acid terminology. All right, let's move forward. Strong versus weak. We are taking a look at the difference between a strong acid and a weak acid. Now know that this has nothing to do with concentration, at least not like the molarity of the acid added to solution. This has to do with dissociation. So when I add a strong acid like hydrochloric acid to water, it is going to dissociate completely into hydrogen ions that then become hydronium ion and chloride ion, right? It's a forward reaction. When it's all done, there shouldn't be any hydrochloric acid left in the solution. Everything is going to be hydronium and chloride. Whereas with a weak acid, so we're going to use HNO2. This is actually going to be written with equilibrium arrows because it's an equilibrium reaction of sorts. So if I add HNO2 to water, some small portion is going to turn into H3O plus and NO2 minus. But actually, if you're going to look at the equilibrium constant, it favors this side of the reaction. So there will be more hydrogen present in the solution, which is why we consider it an acid. However, it's a weak acid because some of it stays in its full form rather than dissociating. So that comes to our conclusion, or what I've written up here, that strong acids are going to dissociate completely and weak acids are going to dissociate partially. The difference for us between a strong acid and a weak acid is what species are actually in the solution. What's going to be in my solution if I add a strong acid is going to look different than if I have a weak acid. When we look at a strong acid, we're going to use the generic form, well, for strong and weak acid, of HA. The H being the acidic hydrogen and the A standing for the conjugate base that is produced there. Here, if we look here, we have the hydronium ions that are produced from the acidic hydrogen, and we have the conjugate base. Those are really the only two things, in addition to the water, of course, that are in the solution of a strong acid. However, if we look at a weak acid, there will be one additional species in the solution. The acid itself, undissociated, will be dissolved in the solution. So with a weak acid, we'll see the hydronium ion, the conjugate base, water, and the undissociated but dissolved acid. The next step we're going to take is to quantify the rate of dissociation for a weak acid. We quantify that with, of course, an acid dissociation constant. This is the quantitative measure of the strength of an acid in the solution. It's the same thing as an equilibrium constant for a chemical reaction, but it's in the specific context of an acid-base reaction. So if we look at our dissociation reaction, we can take that, put products over reactants, and we end up with this format here. It's important to notice that you have water. Water, because it's a liquid, doesn't actually end up in the dissociation constant. So an acid dissociation constant has the H plus concentration, it has the concentration of the conjugate base, and then on the bottom it has the concentration of HA, the acid itself. If we take a look at a strong acid, we're not going to have an acid dissociation constant because everything is going to be up in our H3O plus and our conjugate base Cl minus here, and we're going to have a 0 down here representing the HCl. So this is not possible, okay? Whereas if we have a weak acid, we will have a substantial amount down here in the HF concentration, and there will be a substantially smaller concentration up on the top. So when you're looking at Ka values, they're going to be, generally speaking, substantially less than 1. Now you're going to ask, so how do I know if an acid is strong or weak? By looking at it. You know that by memorizing the strong acids. Here's the list. You need to know them. Memorize them. Then, if you're looking at an equation and it doesn't match one of these guys on the list, then we know it's going to be a weak acid. Okay, so anything that is not one of these acids, there are 7 of them, we are going to consider a weak acid, and you should be able to find a Ka value for that acid. If it's on this list, there will be no Ka value. That brings us to the end. Hopefully you caught the difference between the two definitions of acids and bases. You should be able to identify a conjugate acid and a conjugate base in an equation, as well as explain the difference between a weak acid and a strong acid in terms of their dissociation. Thanks for listening.